So, greetings, students. In today's lecture, we will be dealing with your short circuit capacity, and another one method we'll be seeing with respect to your short circuit fault. So, in last lecture, we have covered about the formation of your Z bus. So, using your Z bus, you can find the fault analysis. You can carry out the fault analysis. It is one of the method. So there I have stopped up to your bus building algorithm. How to build your bus we have just discussed. Okay. So before getting to the problem of finding your short circuit fault current, okay, you have to know about this particular term, that is short circuit capacity. SCC they will be defining. So first you have to know about what this short circuit capacity implies. Okay. So the short circuit capacity is nothing but it is a common measure of, so SCC is a common measure of strength of the bus. Okay, so it is a common measure of strength of the bus. Okay. And over here the short circuit we will be representing in terms of MVA. Okay, so if we are representing in terms of MVA, in the sense the short circuit MVA at bus K, that is, you are considering a bus, and for that particular bus, what is your short circuit value in terms of MVA you have to see. Okay, so short circuit on SCC will be equal to, we are speaking in terms of MVA, will be equal to, so it is a more or less same as that of your apparent power. So apparent power only as the unit of VA. Okay, and over here this power becomes root 3 B. Okay, root 3 V L K I K. Okay, I K into F, I K of F, that is fault current, into 10 power minus 3. Okay, into 10 power minus 3 MV. So this is the formula. So this is for short circuit capacity. Okay, so what purpose this short circuit capacity is used? It is the common measure of strength of the bus. That is, how much amount of power that particular bus can be able to hold in case of a fault arises. If a fault arises, there has to be a limit that the bus can able to hold it. Okay, so that limit is particularly given by this value of SCC. Okay, and now over here this VLK represents your line voltage. Okay, so VLK represents your line voltage in kilovolt. Okay, and followed by your IFK is nothing but symmetrical three-phase fault current. Okay, I hope you got the no the value of SCC. Now the question arises. So how it is possible to find the value of your IFK? Okay, so IFK is your fault current. So it is necessary to find your fault current. Okay, so your fault current you can represent with respect to your per unit. So that is per unit representation. You can represent your fault current as VK 0 divided by XKK. So which is nothing but the derived from your Ohm's law. So it is derived from your Ohm's law. Okay. That is, your fault current is equal to the voltage, the initial voltage. So here 0 represents your initial voltage. So initial voltage by your yeah, impedance value. Okay. And over here, as I said, this Vk of G0 is your initial, so which represents your pre-fault voltage. Okay, it is nothing but your pre-fault voltage, pre-fault bus voltage. So it is also in per unit, in per unit. Okay, so after this, your XKK is nothing but the per unit reactance. It's nothing but a per unit reactance. Okay, so now we have got the value of the fault current. So before that, you have to know about how to find your base current. Okay, you might have in the question they will be giving your base power they will be giving, followed by your base voltage they will be giving. Okay, so using these two parameters, how we can find your base current means their base current value will be equal to IB, which is equal to, as you know, with respect to the apparent power, it is SB by here into 10 power 3, and over here it will be, we are speaking about a three phase, so it will be root 3 VB. So this is how you can find your base current. Okay, it is simple formula as you know. So here your base power is SB and your base voltage is VB. From these two parameters, you can easily find. So it is a line to line voltage. Okay. So using this, you can easily find your base current value. And now we have represented your fault current in terms of your per unit representation. Now you have to represent that in terms of your base value. Okay, you have to represent in your amperes. You have to represent in your amperes. So in order to represent the ampere, the fault current in amperes, fault current in amperes is given as, the fault current in amperes is given as IK F. Okay, so this is what in amps. So now we are speaking about amps, which is nothing but your per unit value into the base value. So you have to multiply your per unit into your base value, what we have found, IB. So for, with respect to this, it is very easy to get your value of fault current in amps. KF equal to, so this value remains the same. So over here you have to substitute. So it will be VK, that is the pre-fault voltage, by XKK into, so over here it will be E by root 3 into VB into 10 power 3. Okay, so this is the fault current. We are speaking in the unit of amperes. Okay, And now if you are putting substituting this value, okay, this value in the formula of your short circuit capacity, that is SCC. If you are substituting in SCC means, that is short circuit capacity, what happens, we'll be getting the value of this value remains the same, Vk, that is the nothing but your pre-fault voltage, Ek of 0, so into SB, it will be SKK, and followed by, so there was a VL, right? So there was a VL. So over here you can see, so this is your VL, okay, line voltage, and you'll be multiplying with that. Okay, so it will be into B. So root 3 also will be there, right? So root 3 will be there. So it will be root 3, and over here it will be root 3 into VB, and it will be into VL. Okay, so here there was a 10 power minus 3 and 10 power 3. That is, you're substituting in your SEC formula this value of IF, IK of F. Okay, so now what happens? This gets cancelled, this gets cancelled, and these two gets cancelled. So you'll be getting the short circuit capacity SCC to be Vk of 0 divided by XKK. Okay, and now here comes the SB into VL by VB. Okay, so this is the value of your short circuit capacity in terms of VA. So this is in terms of VA we are speaking. Okay, but we are considering two assumptions. Now we have to consider two assumptions. Consider two assumptions. So the first one is consider the VL equal to VB. That is, your line voltage to be the same as that of your base voltage. Then your SCC, in most cases, it will be equal. Okay, so your SCC will be equal to Vk. So these that two becomes equal and get cancelled out. So SB by XKK. Okay, and the second condition is consider the pre-fault voltage. Consider the pre-fault voltage as a flat, that is to be a flat voltage profile. Okay, pre-fault voltage to be a flat voltage profile. So if it is a flat voltage profile, in the sense you will be getting Vk of 0 to be 1. Okay, and now your SCC will be equal to SB by XKK. So these are two assumptions. Okay, if you are not considering the assumptions, what you have seen in the previous slide is the value of your SCC. Okay, so now the unit over here, it will be MVA. Okay, so this is what with respect to your short circuit capacity SCC. And the next one what we'll be seeing is, we'll be dealing with the method. Okay, we'll be dealing with the method of finding the fault current using, okay, finding the fault current using your Thevenin's method. Okay, by two method it is able to can easily form it. First one is your bus building algorithm, how we can find the fault current. Okay, I have covered your bus building algorithm methodology, I have covered. So the fault analysis I will be covering after taking your Thevenin fault analysis. Okay, and now we'll be moving to the formulation of the Thevenin fault analysis. So for the Thevenin fault analysis, it is the most similar to that what we have seen with respect to the circuit theory subject. The same thing will be there. So how we so basically what happens is you have to know that the ultimate objective of the problems in this unit is you have to find your short circuit current. So that is your ultimate aim in this subject. And okay, so now we'll be dealing with respect to your short circuit analysis using Thevenin's theorem. Okay, so now we will be seeing using Thevenin's theorem how it is able to find the uh, fault current. Okay, how we can find the fault current you will be seeing. Okay, so the first step is draw the draw a single line diagram of the entire power system network. Okay, so on the single line diagram, indicate indicate the capacity rating, voltage, resistance, and reactance. Okay, of all generators, transformers, and transmission lines. So this is your first step. Okay, so step two. So the what we have seen with respect to the unit one, the same thing. You'll be selecting a common base, right? So that's your second step. So select a common bus that is common base value, base MVA, SB, and base KV, and all the impedances to convert all the impedances to per unit values on the same base value. So this is your step two. And for step three, corresponding to single line diagram. So corresponding to single line diagram, draw reactance or impedance diagram. Okay, or impedance diagram showing one phase of system and neutral. Okay, so now on this, so again step 3, on this diagram indicate all per unit resistances and reactances of components calculated in step 2. Okay, step 4, and it is a important step with respect to your short circuit analysis. Calculate the total per unit impedance, from faulted point, from the faulted point through the source using the concept of electrical circuit analysis. Okay, so for this you can make use of a series parallel combination, that is in order to find the value of the total impedance. So series you can make use of. Okay, and followed by that parallel, that is you are finding the equivalent impedance. So series impedance or parallel combination. Otherwise you can also make, if there exists a transformer, you can make conversion of star to delta conversions also. Okay, so these represents nothing but so these represents your concept of electrical circuits that you have to follow to get your total impedance. So here the total impedance, what you will be getting is, total impedance will be ZTH. Okay, and for finding the fault is your step 5. So in the step 5, determine SCC. Okay, that is short circuit capacity. So how we will be doing that, I will be telling. So for here, at initial stage, you have to draw your uh, what you can say. You have to draw your Thevenin equivalent circuit. So it is VTH. So this will be your VTH followed by ZTH. Okay, so followed by your ZF. So that is a fault impedance. Okay, so after this, the current flowing in this entire loop will be your fault current. That is your IF. So it is our ultimate aim is to find your IF. Okay, IF finding is your ultimate aim. So as per the Thevenin's rule, your fault current IF will be equal to your voltage, Thevenin voltage, VTH divided by ZTH, okay, plus ZF. Okay, this is the value. And through this, if you want to find the ACC, you have to apply the same formula what we have seen before. That is SCC. Okay, for a three phase, it will be equal to SB by ZTH. So this is what we have seen in the previous case. Okay, the same thing will be coming over here. So over here, the another one particular point you have to check it that this ZTH will be in per unit, but this will be in the value of a common base MVA. Okay, and hence your SEC value will also be in the MVA unit. Okay, so while dealing with the problem, I'll be explaining, so it will be very easy for you to understand it. And okay, so this is what with respect to your Thevenin's method. So next is about Thevenin problem. So that I'll be covering in your next class. Okay. So thank you, students. With this, I'm just winding it. Thank you.